Hi, my name is Tuyet Wu. This is my red ID. So we're given this diagram of a beam and we're asked to find the principal stresses and the shear max at point A. So to find the principal stresses and the shear max, we first need to make a table. Actually, I'm getting ahead. First, we need to draw a cut of where point A is. A diagram of a cut where point A is. So that is this right here is point A, and we're given an axis of, this is our y, moment in y, our reaction in the x direction is right here, and our moment of x, and this right here is our reaction in z, and our moment in z. Our forces are the same, and everything else is the same, just the cut. There's a cut when point A is. So next, I'm gonna make a table of the load for the load in order to find the direction of I, J, K for the R, vector R, and same thing for the force. We're gonna find it in the I, J, K, and the moment in I, J, K. So first thing first, we're gonna find it for the 750 Newton. I'm gonna look at my diagram. So for the 750 Newton, I kind of drew the arrow. It's supposed to go down, not to the side. So it's going down. So for the 750 Newton, in the x direction, so this is the x direction, which is the I, it's 180. And then in the j, which is right here, 16. And in the k, it's 0. Next, for the force, we just have one force acting in the j direction. Since it's going down, it's a negative 750, and for the k direction, 0. Next, I'm going to do the 500 Newton load. So 500 Newton load is right here. It's from point A to here, which is just this, adding 180, add 40, which is 220. And then for the j direction, there's nothing. For the k, same thing. Next, for the force, we'll have, so the 500 is going this way, which is the k direction because it's going towards the z. So it's 0, 0, since it's going this way, it's positive 500. So lastly, 10,000 Newton. So 10,000 Newton is right here. It's in the x direction with the I direction, it's just 180, adding 40 is 220. So there's nothing in the j direction, and there's nothing in the k direction. So next, when I do the force, so for the force, we're just having it going towards the x axis, which is I, and it's going towards the positive x direction, so it's positive 10,000. So 0, 0. Next, moment. So for moment, it's just the cost product of R and F. First, for I, it says 0. Same thing for the J, and for K, we have negative 135. And then next, we have 0, and then we have negative 10, 110, 0, and down here it's all equal to 0. So next, we're gonna find the reaction in the moment of x, y, and z. To do that, we're gonna use equilibrium. So Rx, Ry, Rz, Mx, My, Mz. So since we're using equilibrium, since this is positive 10,000, we're going to have a negative 10,000 to cancel out the positive 10,000 to make it equal to 0. And then down here, we're going to do the same thing. Negative 750, positive 750, positive 500, negative 500, 0. Since it's negative, we'll make it positive to cancel each other out. And positive 135. So from this, we know that mx is equal to 0. And we're going to try to find the longitudinal direction. So right here, the longitudinal direction will be along the Rx. So therefore, the moment of x, for the mx, there's no longitudinal moment, so there is no torsion for this problem. However, right here, we do have the value for Rx, and this is our longitudinal direction. So for our longitudinal direction, so we're going to solve for Rx, we're just going to go in order. So we're going to solve for Rx, since it is along the longitudinal, it's going to be our axial. So for the angle view, we can look from neither latitudinal direction. So I'm gonna look at it from the z and x direction. So z is gonna be down here, x will be right here. So right here, A will be right here. So going this way, it's the positive x direction. So since we have a negative 10,000, our 10,000 can be this way. 10,000 Newton. So to solve for x, we're going to use the stress formula over A. A is the area, P is just our reaction. So we have a negative 10,000, and this negative will cancel out, so we get a positive 10,000. Our A will be, so we have 60 times 32, that's our area, 60 times 32 millimeter, and we will get 5.21 megapascal. So I'm going to use a separate sheet to draw our stress blocks, because that will be easier for me to combine them in the end. So Rx, which is our axial, and we have stress block. Oops, I messed up. We will have our xy plane, xz, and zy. So we have 5.21 megapascal for the stress in x. So since it's positive, we're going to have tensile stress, so that's positive tensile. So positive 5.21 megapascal. Same thing here with this one, 5.21 megapascal in tensile. So next, we're gonna do ry. Ry, since it is in the lateral direction, it's going to be a transverse shear. So for the angle view, we're going to look from the lateral direction the force is not acting on. So we're going to have our A up here in the corner, and our X direction, and our Y direction, and our reaction, which is a negative 500, so it's got that. So the formula we're going to use is shear equal VQ over IT. So first we're going to try to find Q. Q is the y bar prime and a prime. A prime is the outermost area, and y prime bar prime is the distance from the neutral axis to the centroid. So in this case, since due to our location of point A, our outermost area is going to equal to 0 because there's nothing for us to calculate. So therefore, the outermost area is equal to 0, making the shear stress for at Ry equal to 0. And we have nothing to graph in our stress block, so I'm not going to go to that sheet. So next, no, paper. So next we're going to do our RZ. So RZ, since it's a lateral direction, it's in a lateral direction, it's a transverse shear. So for our angle view, we're gonna look from the lateral direction the force is not acting on also. So we're gonna have the Z going direction and the X direction, and we're gonna have 500 Newton. So our shear, same formula, VQ over IT. So first, we're gonna find I. I is this 1 over 12 base height cube. We're gonna plug in everything. We're gonna get 0.06 cube times 0.0232, which is equal to about 5.76 to times 10 to the negative 7 m7 to the 4th. Next, we're gonna find Q. So I'm gonna look at the end view of the beam. So A is right here, and right here is our neutral axis. And right here is equal to 0.06, and down here is 0.032. So Q is equal to y bar prime times the outermost area. So y prime is the distance from the neutral axis to the centroid. Our centroid is right here, and y prime is just from here to here. So we're gonna take half of this, so 0.06 divided by 2, which will give us this distance, but that's not what we want. We want this distance, so we're gonna divide by 2. So 0.03 over 2, which is our y prime, and we're gonna multiply it by the area, which is 0.06 times 0.032. will give us 1.44 times 10 to the negative 5 meter cubed. So when I plug everything in, sigma equals 500 Newton times 1.44 times 10 to the negative 5 meter cubed. And down here, cube is equal to 5.76 times 10 to the negative 7 and 4 times by the thickness. The thickness is just 0.032, and that will get us 303.90625, which we can convert it to which we will convert to megapascal because that's what we've been using for the stress block. So 0.391 megapascal. So when I draw that in a stress block, sorry. So stress block for RZ. So it's our shear. So shear. So it's gonna go right here in the XZ plane. Since it's positive, it's gonna go like that, 0.391. Nothing in the other two planes. So next we're gonna do moment, since we don't have anything for moment in X, which is the torsion, we're gonna go next on to moment in Y, moment in Y. Since it is in a lateral direction, it's gonna be bending moment. Or for angle view, it's gonna look down from the axis moment, the axis of moment is acting on. So it's gonna look like this. Our X direction and then our Z direction, and our A will be right here. And we're gonna have a positive moment of 110, so it's gonna go that way. Newton meter. So I'm gonna use my over I. So for this, since our point A is located in the neutral axis, our y is going to be equal to 0 since point A is located at the neutral axis. And y equals 0, and so the stress in X will be equal to 0. I'm just going to pause a moment. My mom just came home. Okay, so we're going to have nothing to draw on a stress block, so then yes. Next, our moment in Z. So moment in Z is a bending moment because it is the lateral direction, so it's going to be a bending moment. So for angle view, it's going to be the same as the MY bending moment. We're just going to look from the axis moment, from the look down from the axis moment it's acting on. So it's going to look like, so X is positive, and then we have direction of y. And then our A is located up here, and we also have a moment of 135 Newton meter. So when I use the same formula, my over I, so I'm going to plug everything in. 135 Newton meter multiplied by the other y 0.032, and oh, wrong one, not that. Y is equal to so y is equal to 0.016, and then I haven't figured out what I is, so I'm gonna find I. So I is equal to 1 over 12 times 0.06 times 0.032 cubed, and I'm going to plug that in for I, and in the end when I get stress in X is equal to 13.180 megapascal, and that will be our last stress block drawing before we combine them. Moment in Z, which is bending. Right here is transverse. So gonna look like ZY, ZX, Y, XY, and then it's gonna go this way because it's positive, therefore it is tensile. 13.18 megapascal. So I want to combine the stress block into one whole one. So since both of them are in tensile, we can add them together. So it's going to be equal to 18.39 megapascal, and then ZX, we will have the same thing. We can add them, 18.39 megapascal, and we'll have a shear stress right here, 0.391 megapascal, and we have nothing in the ZY plane. So when I use that to find, so when I use the XZ plane, because we have the most known variable and it's the most compact plane, so it's easier to find a principal stress using stress in X. The stress in X is equal to 18.39 megapascal, and then the stress in Z, we have 0 because there's nothing, and then for the shear XY is equal to 0.391 megapascal. So we have everything we need to find the shear stress, the principal stresses and shear max by using the formula of shear max. When I find shear max first, is equal to X subtract shear stress of Z all over 2 square, adding shear XY square. So I'm going to plug everything in, and we get 18.39 0.39 subtract 0 over 2 square plus 0.391 square. We're gonna get about 9.203. But for this, I'm just gonna do 9.20 megapascal. So next, for the shear max. So I'm gonna find principal stress of 2 is equal to x plus z over 2 plus or minus just this. X subtract 0, z over 2 square plus shear xy square. So plugging in everything, 18.39 plus 0 over 2 plus or minus 18.39 plus 0 subtract 0 over 2 square plus 0.391 square. So in the end we get 9.195 plus or minus 9.20 MPa. So we get shear max 1 equal to 18.395. S2 is equal to, so subtract those and we get negative 0.005 MPa, MPa, and then from up there we get shear max of 9.20 MPa. Signing off. And that is it.